Okay, our final speaker of today afternoon session is Fedor Vylegzhanin from High School of Economics. He's going to talk about the commutator subalgebras and subgroups in toric topology.
Yes, thank you. First of all, I want to thank the organizers for letting me speak at this wonderful event. And then I want to confess that style 2 is not exactly right, because I want to speak about, well, one day I want to speak about loop homology of quasi-toric manifolds and fundamental groups of their real analogues. But today I will speak about loop homology of moment-angle complexes and fundamental groups of real moment-angle complexes. So here, in fact, I should put homotopy theory of polyhedral products. So let me start with polyhedral products. As we already know, we start with a sequence of pairs of topological spaces. We need m such spaces. And with a simplicial complex on m vertices. Then we can take the following union, which would lie in the product of xi's for each simplex of k. We can write down products of xi's on places that correspond to elements of I, and products of ai's on all other places. So this would naturally be a subset of this Cartesian product, and it is called a polyhedral product of x and I. So we want to study these spaces, and one important and well-studied example is the case when X is a pointed topological space and A is just the base point. So we can take such polyhedral products, and this naturally embeds into a Cartesian product of xi's. So then it is a well-known theorem that the homotopy fiber of such map is also a polyhedral product form C omega x power of k. I don't even know the authors of this theorem. And also this map, let me call it J. And also omega j has a section. And what we are trying to do is to study the homotopy type and homotopy invariance of such spaces using these fibrations, because such spaces are much easier to study. And we want to restrict ourselves to the case of flux simplicial complexes. So then it is especially simple. So I recall that K is flag if the following condition holds. Whenever we have a set of vertices that are pairwise connected by edges, it is a simplex. So then there is a literature essentially two stories that are well studied. First story is the case when all xi's are simply connected. Sorry, P1 of xi is trivial. Then we can study, for example, loop homology of such spaces, and loop homology is an associative algebra. So there's some theory about connected graded associative algebras. In terms of homology of loop spaces with respect to contrarian product. And for us, the main example will be the case when all xi's are CP infinities. So then this fibration looks as follows. The fiber can be identified with so-called moment-angle complex, Zk. The total space is CP infinity point to the power of k, so-called Davis-Janusz space. And the base space is CP infinity to the power of m. So this is what we will study today in the first half of the talk. And the second well-studied case is when all of these spaces are aspherical. So I can write down like this. So then these spaces are controlled by group theory, and these three spaces are also controlled by group theory, as we will see. So here we have groups. And here we take xi, for example, rp infinity, which is spherical. And here we have real analogs of such spaces. The real moment-angle complex, the real Davis-Yanushkevich space, and the mth power of sub infinity. I'll just write it like this. So I don't have much time, so for the rest of the talk, we restrict ourselves to these two examples, but everything can be generalized to this case or to this case. But currently, we do not know what happens if X is arbitrary, if X is not spherical and not simply connected. So maybe this would provide a unified approach to what I'll talk later. So let me start with the first story. So this vibration, when we apply the homology functor, the loop homology functor, it will produce an extension of connected graded algebras. So we have this. This would be not an exact sequence, because the algebra in the center would be a tensor product of the algebra on the left and the algebra on the right. But still, it is called an exact sequence of algebras for some reason. So this is what we have. Here we have loop homology of Cp infinity to the power of m, which is the homology of torus, which is the exterior algebra on m generators. So this is an extension of algebras. And there are results by Panov and Ray on the algebra in the center. So what Panov and Ray tell us? First of all, this algebra is computed in the sense that it is identified algebraically. This is the X algebra with respect to unit multiplication of the Stanley-Reisner ring of R simplicial complex K. So then we can study it by means of homological combinatorial algebra, but still it is not known in the general case. So it is a challenging problem to understand its multiplicative structure. However, we know how it looks in a flag case. So if K is flag, we identify it with a certain partially commutative algebra on M generators. So the squares of the generators are 0, and also some pairs commute. I and Uj commute whenever I and J are connected by an edge. So this is a partially commutative algebra. And this map is identified with the abelianization map. So in some sense, loop homology of moment-angle complexes in the flag case is a commutator subalgebra in this partially commutative algebra. Yeah, for the rest of the talk, K is flag. Yeah, yeah. So now we want to understand the structure of this algebra, for example, to present it by generators and relations. So to describe this as a quotient of tensor algebra by some homogeneous relations. And there are some results from homological algebra of connected algebras. It is important that they are connected, which means that they are graded, augmented, and the augmentation ideal consists of elements of positive degree. So in the case of field coefficients, this theorem is by wall, and I have generalized it to the case of arbitrary principal ideal domains. So let A be an algebra connected over a principal ideal domain K. And we want to understand what can we say about generators and relations of this algebra. So the answer is given in terms of Tor functor. So let me find some place and give a definition. So if I have a finitely generated module of a PID K, then M can be presented additively. So it is a quotient of some free module. And I want to take the smallest possible free module to generate M and take the smallest possible submodule well, to describe the relations. So I write this as gen of M, k to the power of gen of M modulo k to the power real of M. So these numbers, gen and real, are well defined. So gen controls like the size of M, and real controls the size of additive torsion in M. So here we have the following. First of all, any presentation of A by homogeneous generators and relations has at least some generators and some relations. Let me write how many. At least this much generators. This is number of additive generators for the first Tor functor of our coefficient ring as a module over our algebra A. And for relations, we have something similar. So we start with number of additive generators for the second Tor functor, and then add the size of torsion in the first Tor functor. So this lower bound happens for any presentation of a connected algebra by homogeneous generators and relations. Moreover, this bound is always achieved. So in some sense, we can say that how many generators and relations we need to present a connected algebra. Moreover, these bounds are graded. So if we wanted to study how many generators of a degree n we need to present an algebra A, you can show the nth graded component of this functor, because this functor is graded. And this number will give us a number of generators of this degree. This is my first result. And my second result is the calculation of this Tor functor for loop homology of the K in the flag case. Case flag. So then this nth Tor functor can be expressed in terms of combinatorics of our complex K. So this would be just a direct sum of reduced homology of subcomplexes of K. Yeah. So the idea of this calculation in more general case was described by Vylegzhanin in his talk on previous workshop. So I'd not explain it here, but these calculations were done using this extension and using our knowledge of this algebra and this algebra. So this can be done. So what follows from this? It follows that we can say how many generators and relations we need to present loop homology of moment-angle complexes in the flag case by homogeneous generators and relations. So yeah, here, so we have these much generators, where B0 denotes the number of connected components in a simplicial complex, and this much relations, number of additive generators for direct sum of first homology of full subcomplexes of K. So this is the number of generators and relations. Now I want to say, how do these generators and relations look like? This is also done. Number of generators, well, explicit generators were computed by Grbic, Panov, Terry, and Wu. So in a few minutes, I will describe them. So first of all, we need some combinatorial data, like some sets that have this cardinality. So for each J subset of M, I will describe now a certain subset of J called theta J. So let me just draw a picture. So I can order vertices of my for subcomplex Kj from the left to the right. So on the left we have 1, on the right we have m. Let me draw just connected components. So this looks something like this. I don't know how do they look like. For example, let me say that this is a picture of Kj. Right. Then I want to take the smallest vertex in each connected component. So I take this vertex, this vertex, this vertex, this vertex, this vertex. Then I want to remove the vertex from the component which contains the maximum element of Kj. So I removed this one. And then the set of red vertices will be my set theta of j. So of course, this set is by 1 smaller than the number of connected components. So the set of generators can be described as certain elements such that have this and we have this. And by these elements, I will say just some iterated commutators. I'll put here some elements like this, where I can write down such iterated commutators. So Grbic, Panov, and Wu proved that this set multiplicatively generates our loop homology of moment and complexes in the flag case if K is a field. But I have shown that this works over arbitrary commutative ring K with unit. And I have also described the relations between them. So they correspond, as we see, to first homology for subcomplexes. So we need, for example, 1 cycles in such simplistic complexes. So let me just write down a relation that corresponds to simple 1 cycle. So let's just vertices I1, I2, etc. Ik, and then again I1 be a simple cycle in simplicial complex Kj. So each vertex is connected by an edge to the next one. So then to this data, I can write down a certain identity between elements of this form. So just write down this quick. Here are some sum over some thing. So I write down this set as a disjoint union of 2 subsets subject to some combinatorial conditions. And then I can write a commutator of 2 elements of this form. So these identities hold in loop homology of moment and complexes. So what do we do next? These elements are not necessarily the generators. I call them GPTW generators. But we can actually compute these elements as polynomials, non-commutative polynomials on these generators. This can be done recursively. So these are computable words. On GPT generators. So we compute them, for example, using computer, and then we'll obtain an explicit relation between these generators. And if we do this for cycles that generate first homology of all simplicial subcomplexes of K, put them all together, we obtain an explicit multiplicative presentation of loop homology for moment and complexes. So this is the main result in this case, and this is the end of the story 1. So if you have any questions on this, please ask them now. So I guess everything is clear or not clear. So I proceed to the story number 2, which is a real analog of what we have seen above. and we will obtain really similar results in the real case. So we start with this fibration, and we ask what happens to fundamental groups. So we obtain an extension of groups by 1. This sequence is actually exact because this space has no P2. Well, pi1 of R pi infinity is the mod 2. So here, just write down this. Yeah. So then results of Panov and Verevkin that we already heard above today, which are based on results of Panov, Ray, and Vogt. So first of all, this group is the right-angle Coxeter group, which can be presented by M generators G1 to Gm modulo the following relations. Squares of these elements are the unit, and also some of them pairwise commute. So this is a presentation of this group. This maps becomes the abelianization. So naturally, this group is the commutator subgroup of this group. And if K is a flag complex, then all these spaces are aspherical. So for example, we can compute homology of these groups because it is the homology of these polyhedral products, and we know how to compute homology of polyhedral product, for example, using BBCG decomposition. So now again, we want to study this group, to study its presentations by generators and relations, and we want to have a homological lower bound of number of generators and number of relations. There is indeed such bound. It is an exercise in the book of Brown on cohomology of groups. So let G be a group. Then each presentation of D has at least some generators and some relations. So let me write down how many. In my notation, we'll have the following: number of additive generators for first homology group of G with integer coefficients. And here we have also the same formula. But this time, this bound is not always achieved. For example, if G is not group, fundamental group of the complement of a knot, then this group is always infinitely cyclic. So it is isomorphic to Z, and this number is 1. But not all knot groups are presented by, are not cyclic. Not all of them are cyclic. So this bound is no longer strict. But however, we can use it to obtain something about generators and relations here. So I can write down the well-known result about homology of this group, or of real moment complex. So we can say that this is in brackets because this formula holds even for non-Fedor complexes, but for non-Fedor complexes, we do not have an interpretation of this in terms of groups. But still, let me write down this. This is also the same direct sum. Reduced homology of all four subcomplexes of K. So this is well known, and we can identify this with group homology. We can also use the algebraic definition of group homology to write down this as a Tor functor. And we can also identify the group ring of a group with the homology of this group as a topological space. And this is the loop space on its classifying space. So I can write down that this is Tor for loop homology of classifying space for this group. So I can put the real moment analytical complex here. So we can see that this is equal to this. No. So the reason is because in this theorem I use integer coefficients to bound presentations of groups. But this holds, of course, for any k. So I just want to apply it here. Yeah, but this result holds for any ring, and this result holds also for any ring. So I leave it here, and we have the consequences of this. So have at least this much generators. And at least this much relations. So this is a lower bound, and we want to have an upper bound. And well, I have an upper bound, but it does not match the lower bound in the general case, but it matches in special cases. So let me introduce some notation. For a not connected topological space, I denote by phi1 big of x the free product of fundamental groups of its space components. And for a discrete group G, I denote by rank of G the minimal number of generators for this group. So then theorem, this is a work in progress, but still it is proven. So this group has a presentation by this amount of generators. And here I have a non-abelian analog of this. So if we want to take abelianization of this group, we'll obtain the first integer homology of Kj by Poincare-Hurevich theorem. So this number is always not less than this number, and it matches, for example, if all these fundamental groups are free or free abelian. So in many cases, these bounds match, so we know exactly how many relations we need to present this group. And I have 2 minutes to explain how do these generators and relations look like. So I hope to write down some formulas. Yeah, so there is 2 options how to describe the generators in this algebra. So first option is given by Panov and Verevkin to use just the same formula, and it works. So this time we still have iterated commutators in the group, but instead of ui's, we have gj's. Another option was suggested by Litsai. So I denote these generators delta jj. We can write down them like this. So take the product of ji's for all I and j in the ascending order. Then multiply this by jj inversed, then multiply by products of all other elements inversed. So this element belongs to the commutator subgroup of the right angle Hochster group, and I denote it by delta jj. So this is a description of generators, And you can also describe relations in similar terms. So I start with the same cycle, and I can write down the following product of some computable words. Once again, these elements are not the generators because this is not necessarily is in theta, but still we can compute this somehow. So to any cycle like this, the following relation corresponds. So as you see, we have really some mysterious parallel between results in theory of algebras and theory of groups. Some results were known. These results are new, but still mysterious. So that's when I wanted to end. Thank you for your attention.